Hello, thanks for choosing to watch our presentation. My name is Afshin Salek, and I'll be doing this presentation with my colleague Fio. We are both members of Redis team at Uber. I will start by giving an overview of how Redis is deployed at Uber. Then I will talk about our current data replication technology to provide some background and set up the context for the second part of the talk. Fio will then take over the rest of the presentation to talk about the next generation data replication. Let's start by some high-level overview of how Redis is deployed at Uber. Redis team at Uber offers Redis through a Redis as a service model to the rest of engineering. Currently, the main use case is in-memory distributed cache to front our persistent storage solutions. Our deployment model is to use 2M proxy as the sharding and routing layer in order to be able to horizontally scale Redis. Internally, we call this T-Redis. Just as a quick introduction, the way 2M proxy works is that you would create a pool of back-end Redis servers and then export the pool using a single access port. This gives the illusion of talking to a single server to the clients. So when a user provisions a Redis instance through our self-service portal, a bunch of Redis nodes are allocated, and then a 2M proxy pool is created to represent those Redis nodes. There might be a terminology mix-up here with regard to how we use the term instance. So just to emphasize, a Redis instance refers to a collection of Redis servers, not just one process. So how are all these different components organized? As you can see in the picture, Redis nodes run on storage hosts and services run on separate compute hosts. There are two things that I should mention here. The first point is about the placement of Redis nodes. In order to minimize the effect of host failures on Redis instances, each host can only contain one node of any given Redis instance. The second point is that we run 2M proxy on all compute hosts in order for services to have access to their Redis instances. Here are some rough numbers showing the size of Redis deployment in Uber. We have about 1,000 Redis instances, and these 1,000 Redis instances have about 11,000 Redis nodes and cover about 50 terabytes of memory and serve about 30 million queries per second. So before talking about replication, let's see how things look in the non-replicated setup, which is the default mode. We have global instances with DC local clusters. So what does that mean? A global instance is a collection of disjointed Redis clusters in one or more data centers, which are accessed using the same Redis URI. So the only thing that makes the instance global is the global URI, which would enable us to do transparent data center failover. Let me explain things using an example. Let's say instance X belongs to service A. Instance X being global means that service A uses the same URI to access instance X in both DC1 and DC2. DC local cluster, on the other hand, means that service A instances running in DC2 only have access to Redis cluster B, as you can see in the picture. So if DC2 fails, it will have no effect on service A instances running on DC1 in terms of data availability. However, this cluster isolation, meaning the lack of data replication, has some issues, including a cold cache start after a DC failure. So how can we replicate the data between the data centers? Remember that I mentioned a 2M proxy pool is a collection of Redis backends. So why not include all the Redis nodes from all the data centers in one pool, so data is automatically sharded by 2M proxy across the DCs? Let's examine this idea. As you can see in our non-replicated setup, the 2M proxy pool in each region only includes the Redis servers residing in the same region. Now, if we go with this solution, it means including cluster B nodes in the pool of 2M proxy running in DC1. Sounds simple and obvious, right? Well, not so much. The problem is that although this is possible in theory, it wouldn't work in practice due to having a mix of low latency connections to cluster A nodes and high latency cross DC connections to cluster B nodes. So now let's have an overview of our current replication technology to set up the context for the next version, which is the topic of this session. There are three main components involved in our data replication architecture. And just as a quick overview, here with more data. So we have three main components. There is a Redis Tailor, which is an Uber component. It's a daemon written in Go that implements Redis replication protocol. There is Apache Kafka, which is a data streaming service. And there is Apache Flink, which is an engine for stateful processing of data streams. Kafka and Flink are open source components, so I'm just going to focus more on the Redis Tailor here. So what does the Tailor do? It replicates from its corresponding Redis server. It batches the commands and then writes the batches to a Kafka topic. What it doesn't do is that it's currently not replicating every command, meaning we only replicate Redis string data type. This is because we haven't implemented any type of conflict resolution mechanism yet. However, the set of replicable commands are configurable. So once we have a conflict resolution mechanism in place, we don't need to make any code changes to the Tailor to replicate additional commands. We've also made some choices in order to have fast and efficient replication. For example, we don't replicate larger than 1 megabyte set commands. Also, if Tailor has to reconnect to its corresponding Redis server, the RDB will be discarded. So let's see how the replication works end to end. The Tailor has established a replica connection with its corresponding Redis server. So Redis server is replicating the commands it receives to the Tailor. Tailor filters set and delete commands and throws the rest away. Then it batches them and writes them to a configured Kafka topic. The Flink job in the remote region reads these command batches from Kafka and writes it to the target local Redis instance. You notice some strange commands here in step 4, which I'm going to explain in the next slide. By the way, I should note that the same setup exists in the DC2 to DC1 direction. So this is a two-way replication. As I mentioned, we have a two-way replication. So how do we break the replication loop? That's where those strange commands come to the picture. As you saw in the previous slide, in the step 4, Flink renames set and delete commands to uber norep set and uber norep del before sending them to the intended Redis cluster. Now, our Redis servers run with a module which basically disables replication for these special set and delete commands. Here I have an excerpt of the module code for uber norep set, which as you can see is really simple. The trick here is in the V string, which is missing the bank character. Omitting the bank character means this set command wouldn't be sent to the local tailor, and therefore we wouldn't have a replication loop. So what are the limitations of this solution? As we saw, it currently only works with the string data type, although this is really not a limitation of the framework, but only due to lack of conflict resolution. The other issue is that we are not replicating large commands. Also, we are only providing weak consistency. So why have we started looking for an alternative architecture? It mainly has to do with the Kafka and Flink component of the current solution. The first problem is the operational aspect, meaning that Kafka and Flink dependency makes provisioning complicated, and we can make it fully automated at this point. It also makes debugging harder. The second is the performance aspect, meaning that replication performance is a bottleneck. So we cannot serve the same level of load to services when cross-DC replication is involved. The third problem is the cost of the solution. Kafka topics are literally expensive, while we don't really need a persistent stream solution for providing cross-DC replication. This concludes the first part of our presentation. Now I hand it over to Phew to talk about data replication using Redis Streams.
Hello, my name is Pyo. I'm a software engineer at Uber, and I work with Efshin in the Redis team at Uber. I hope everyone is staying safe at home. Let's get started on cross data center replication V2. Before we jump into it, I would like to give a brief refresher on Redis Streams. Redis Streams are a data type introduced in Redis 5, and a stream is a key inside Redis, so all the data in the stream are stored in the same key. Some of the commands supported for streams are add, read, range read, and delete. I also want to talk about consumer groups, which are a stream concept for doing checkpointing and for coordination between the consumers so that the same entry from the stream is not sent to more than one consumer. The consumer groups maintain the checkpoint state inside Redis itself using a concept called pending entry list. And some of the consumer group commands are exread group, acknowledge, pending, and claim. So pending is used for reading the entries that have been sent to the consumers but that had not been acknowledged yet. Claim is used for claiming the pending entry of another consumer. We'll discuss more about this later in the slides. For V2, we simply replace Kafka with a Redis cluster to write the Redis streams, and Apache Flink with a lightweight Golang application called Stream Consumer Service. Let's dive into the producing part. I want to mention a very important concept of Redis streams. A Redis stream is a single key inside Redis. What it means is that if we use a Redis cluster, the data inside a single stream will not be sharded into multiple nodes. It's a key and therefore it will stay in a single node. So the publisher application needs to shard the data into multiple streams in order to scale up. If not, all the data will end up in a single Redis key, which is not great. For us, we achieve this by creating queues inside Tailor and we map each of these queues into a stream key inside Redis. Let's take a look at the command flow. When the commands come in, we shard the commands into the queues, and then we batch the commands in the queues based on size and time duration. After this, we send these batches to the map streams. So the command we use is xadd, and if you look at the sample commands, we use xadd and then the name of a stream that we are publishing the data to. And the star here signifies that we want Redis to create the ID for the entry, and message is just a static string key, and batch is the batch of commands. Now, let's take a look at consuming data from Redis. As I mentioned before, String Consumer is a lightweight Golang application. It just continuously pulls from Redis Streams and unpack the commands and apply them to the local string proxy, which eventually writes them to the Redis nodes. Looking at the pseudocode here, we constantly pull, and all the capitalized words are Redis stream keywords. Here we can see X-ray group. We provide the group name and consumer name. Block 2000 means we will block and wait for 2 seconds if there are no entries in the stream. And we read up to 512 entries. And then we provide the names of the streams that we want to consume from. And the greater than sign at the end is a special character. It means that send me the messages or entries that have never been delivered to any other consumers so far. Let's talk about how we use stream consumer groups. We have 2 requirements for consumers. The first one is that the commands need to be FIFO, so that the set and delete commands are in the same order as in the source as we receive them in the source data center. The second one is that the consumer service could go down or get restarted, and therefore they need to be stateless. And we cannot keep the checkpoint data or state in the service. In order to achieve these 2 requirements, we use Redis Stream consumer groups. So a Redis stream could have multiple consumers per consumer group, so that the messages can be delivered faster. However, this does not guarantee FIFO property because some consumers might be faster or slower than others. Therefore, we need to have 1 consumer per consumer group per stream. And we use the pending entry list feature of Redis Stream consumer groups in order to do checkpointing. And it saved the messages delivered to the consumers, but that are not acknowledged in the pending entry list. Once the messages have been acknowledged by the consumer, Redis deletes the messages from the pending entry list. Let's talk about scaling the consumer service. As I mentioned earlier, we need to have a stream delivered to a single consumer thread and per consumer group, and a consumer service can have multiple consumer threads. And also consumer service number 1 and number 2 cannot consume from the same streams. Let's say one instance number 1 goes down or get replaced. The replacement instance or other instances need to pick up the streams that instance number 1 is responsible for. We achieve this by using distributed locks with heartbeats. Each service, when it comes up, claims some streams and put a lock on the streams with a TTL. And then it keeps sending heartbeats to Redis to extend the TTL on the locks. When an instance goes down, the TTL on the locks will expire and other instances or replacement instance will pick up the streams that are not claimed. Alternatively, we could use Zookeeper to keep track of the state. However, we decided not to pursue that route because we want to reduce dependency on external systems. Cool. Let's talk a little bit about some of the lessons learned using Redis Streams. Let's talk about memory management for Redis Streams. Redis has many different max memory policies. Usually, we set this to all keys LRU since we use Redis as a cache. However, we do not want that with the streams. If the max memory policy is set to all keys LRU, the streams themselves will get evicted when memory limit is reached. We do not want that. This might be obvious, but we run into this issue while prototyping. So I just wanted to call it out. And Redis string message retention policy is size-based. With Kafka, you can set it to either time-based or size-based. With Redis, it's only size-based. So Redis will truncate the older messages when the message count limit is reached. We could potentially store or retain more messages, but it will be at the cost of additional memory. Another point is we need to figure out the total memory needed right off the bat based on the throughput that we want to achieve. If the size of each message is way too big, Redis and if the backlog builds up, Redis process will run out of memory. Although we are not hitting the message limit count in the retention policy. If this happens, replication will stop since no more messages can be published to the streams. Another lesson learned is that we can achieve much higher throughput by pipelining the Redis writes in the stream consumer service. Instead of writing one command per request response, we send multiple commands in a single request, so that it's a single I/O event on Redis server side to read all the commands. With this approach, we were able to improve the latency by about 10x under heavy load. And Redis Stream has a fairly large entry size. However, we recommend using smaller entry sizes to keep the latency low. That's it. And let's talk about performance for a bit. Let's look at the performance comparison between Kafka-based solution and Redis string-based solution. We generated test traffic data using memtier benchmark and compared the keys at the end of a benchmark to make sure no data is lost. We benchmark both solutions using a single cache node. As you can see, Redis Streams can achieve about 5x more QPS with smaller payloads or 5x more throughput with smaller QPS. The performance of Kafka-based solution caps at about 23K QPS or 13 megabyte per second. We saw a steep drop in QPS with increased message size for Kafka. However, Redis Streams can push through much higher QPS, and the drop in the throughput is more linear than Kafka. So we're currently working on making the Redis Stream solution production ready. I wanted to call out the team at Redis at Uber. This project was prototyped by Daniel Jiang, our intern, and special thanks to Anders and Bisheng, our colleagues in the team, for their contributions to this project. That's it. Thank you very much.